Okay, so first of all, apologies, I'm quite sick, so if I space out during my talk, I get disoriented, or my voice goes away, then it's probably because of that. Okay, secondly, it's more important that you understand things than me getting to the end, so please ask questions whenever you don't understand something. Okay, so it's going to be about conformally invariant random systems, random processes near the critical point. Okay, so first I'm going to tell what conformally invariant means. What is a scaling limit? So what is a conformally invariant scaling limit? The classical example of this is a two-dimensional Brownian motion. So you hopefully have seen some of that, but I will explain a little bit. Then there will be many other models. Some of them related to two-dimensional Brownian motion, others are not. My focus will be on percolation, because I have worked the most on that. And then I will define the random cluster model, which is, I mean, these models, you will see when I define them, they look very different from each other, but it turns out that there's a unifying model called the random cluster model, which is a joint generalization of many of these. Okay, then I will tell you about a little bit about the Schramm-Loewner Evolution, which is this wonderful tool to compute a lot of things about these models. So whenever you have conformal invariance for a model, which is sometimes known, sometimes just conjectured, but once you have it, you can do computations with this. It's called SLE, so Schramm-Loewner Evolution. Okay, and then if I still have time, then I will also tell a few words about what I'm doing, which is about dynamical and near critical versions of these random models. So that part will be about long and many joint works with Christophe Garban from Lyon and Odette Schramm, who died 5 years ago, and who is the same Schramm as in the Schramm-Loewner Evolution. Okay, so first, you probably have seen a random walk on the integer lattice. Have you? Okay, you can imagine. So you have z squared. You start from the origin, and you flip a four-sided coin and go to one of your neighbors with probability 1/4 each. And then you independently make another step, and so on. So this is the distribution after 6 steps. So of course, after an even number of steps, you can be either back at the origin, which is the most likely thing to happen. You cannot be on any of the neighbors, right, because of parity, but there is some probability here and there is some probability there. So the darker the shade is, the more likely it is that you are there. Okay, and it's kind of clear. You see the square lattice, and it's kind of like a rhombus. Okay, this one is almost the same, just so this checkerboard thing is a little bit disturbing for the eyes. So here I just got rid of the parity issue by first flipping a coin. So with probability half, I will make 6 steps, and with probability half, I will make 7 steps. And this is the distribution of this after either 6 or 7 steps. Okay. Now, after 20 steps, this is kind of similar. You get farther and farther. Okay, you can still kind of see this rhombus, but something seems to be happening. And really, okay, this is my computer is old. Okay, so this is after 100 steps. I don't know how obvious it is, but if you close your eyes halfway, then it's, can you see that it's a circle, really? It's very circular. Maybe here it's less visible, but there it should be completely visible. So you have lost completely the square lattice. I mean, if you look at it from far away, with the eyes half closed, you don't see the square lattice. Okay, so the reason for this is the central limit theorem, which you probably know. So, okay, just the notation. So x1, x2 are the steps, the jumps in the random walk, and Sn is the position I sum over these vectors, for the first n jumps. So these are the positions in z squared. Okay, the jumps have zero mean, right, as a vector. So in both directions it's symmetric. So the mean, the average jump is zero, and the variance, the covariance matrix of the jumps is this. Right? It's kind of, you just compute, with probability 1/4 you jump this way, that way, and okay, and then the central limit theorem is telling us that, well, if you have IID sum of two-dimensional vectors, you know what IID is, right? Independent, okay. Okay, and then you normalize it by the root n and something about the variance, which is this 1/2 here. Then you converge to two-dimensional normal, standard normal. Okay, because this is just 1/2 times the identity, so you converge to symmetric normal. Okay, and well, the two-dimensional normal distribution, that's rotational invariant, right? So even though the jumps are on the z-squared lattice, after many steps, you lose this, and you just see this rotational invariant distribution, the two-dimensional Gaussian. Okay, and more is true. So if you take n steps and look at it as a process, so all the way from one, you look where it goes, and so let's say you look at 2 times t1 times n and t2 times n. So it's somewhere in this interval 0 n, and you look at the joint distribution of where you are at time t1 times n and time t2 times n with the same scaling. Then, well, if you just look at the first one, then it should go just by the previous. It goes to standard normal, except here the time is only t1 times n, and the normalization is still for the entire time. For the entire time. So you converge to a normal with a smaller variance, the smaller variance matrix, t1, and then once you are here, how do you get to time t2 times n? Well, you still have to make t2 times n minus t1 times n in steps, which all these steps are independent from the past. So you really can just think of it as, I'm already here, and then I have to add an independent copy of something else, which is, since I have to make this many steps, it's just a normal with this variance. Okay, so this trajectory that I'm getting is composed of, from far away from this, with this scaling, you add the normal, and then you add an independent normal, and then you add an independent normal, and so on. So it can be proved that what we are getting is two-dimensional Brownian motion, which is it's defined by the property that it's a continuous. So it has to have a continuous trajectory, a random continuous curve, with the property that between a time s, it's normal, it's standard Gaussian with variance. So it's Gaussian with variance s, and it has independent increments. So between time t and time s, you have to add an independent t minus s variance normal. Okay, so really we are converging to this Brownian motion if we are looking at the entire trajectory. Okay, now okay, so at time 1, this distribution is rotation invariant, and at every given time it's rotation invariant. So this entire trajectory is rotational invariant. Okay, this is what, okay, so the rotational invariance of the standard normal implies the same for Brownian motion. Okay, now we got this Brownian motion as a scaling limit of, so by scaling limit is just, okay, so I don't know if it's completely clear what this convergence is. It's kind of well, it's convergence in distribution. So, right, there was those dots, the shading, and you look at it as a measure on the plane, and when you do the scaling, you integrate it against continuous functions, and you get the same integral in the limit here than there. Okay, and so it's a limit, and it's a scaling limit because I have to scale. Time is scaled by n, and space is scaled by root n. I have to right after time n, the random walk went to about root n, and to keep it visible, I have to rescale time. I have to divide by this root n. Okay, so that's why it's a scaling limit, because we have to scale time and space together, which is just the. Okay, now scaling limits are always, so we saw that it's rotational invariant. Scaling limits are always scale invariant. So if I take Brownian motion at time t and multiply it, I just scale it by lambda. Okay. Well, okay, so we got it as a limit, so it's basically the same. It's well approximated by t times n steps of the random walk with this scaling. Now I'm just doing some algebra. I'm multiplying and dividing by lambda squared here, so I didn't do anything here. And here I take down this lambda under the square root. Okay, now if I just rename n over lambda squared to be m, then this is just the same as this, right? So I have lambda squared times t times m by root m over 2. Okay, but this one, well, this is again by being, we had the Brownian motion as the limit. So m goes to infinity. As n goes to infinity, m also goes to infinity. So we get Brownian motion at time lambda squared t. Okay, so really, so being a scaling limit implies that scaling, if you scale space, so you run Brownian motion for time 1, and you multiply it by 2, then it's actually the same, the image, okay, so magnified by 2. Then this is exactly the same as if you had run Brownian motion. It looks the same as if you had run Brownian motion from time 0 to time 4, right? Because the multiplication by 2 in the space is the same as in distribution as multiplication of the time by 4. Okay, by this calculation. So, okay. Okay, now, as we have discussed, Brownian motion has independent increment. And so after, when you stop it at some point and then you let time evolve, you just see an independent copy of another Brownian motion. So you could also do something like you rotate. So if you have Brownian motion, you rotate it around the origin, and then at time 0.42, you look where you are, and around that point you rotate it with another degree. And you could do scalings and rotations with different values at different points. But still, what you are seeing is still just Brownian motion. Okay, so a nice way of making sense of doing some transformation on this Brownian motion, which is locally a rotation and a scaling, but maybe a different rotation at different places and a different scaling at different places, is to apply a conformal map. So I remind you what a conformal map is. So the plane, we think of it as the complex plane. Now, so we have some domain in the complex plane. A function, a complex function, is called conformal if it is holomorphic, so complex analytic, complex differentiable. And it's injective, so one-to-one, and its derivative, its derivative is never zero. Okay, so okay, why is that good? Because okay, so what is the derivative? Well, you hopefully know that it's the best, multiplying by the derivative is the best linear approximation to the function, right? So having a derivative which is a complex number now, f prime z, it means that multiplying by this. Well, how does multiplication by complex number works? Well, you have to scale by the size of the complex number and rotate by the argument of the complex number. Okay, so this conformal map at every point is just scaling by this, locally. It's an approximation, but locally it's scaling by the size of the derivative. Sorry, this is not a prime is missing here. Okay, and you rotate by the argument of the derivative. Okay, so you could say that locally do some and this condition is important because well, if it's zero, then you shrink everything locally into a point. It's like a singularity. You don't really like, but it's not very important. So actually, an injective map can have only a countable number of zeros, right? If you remember from complex analysis. Okay, so if I have Brownian motion and I apply a conformal map, then by this argument, it really should look what I see really should look the same. By looking, it looks the same means that the trajectory is the same, just time is running faster. Okay, right? Because there was this time scaling. Right? If you scale it, it still is like Brownian motion, but with a faster time. Okay, so here is an example, simulation. So this is from 0, 0. This is random walk in the plane, and then you apply the exponential map. Well, the exponential map is well, the derivative is never zero. It's injective. So apply the exponential map. Right, so 0, 0 goes to 1, 0, and right, these negative numbers go close to 0, and the positive real part. Right? So the real axis stays the real axis. The imaginary axis goes to the unit circle. Okay, so I apply this conformal map, and I don't know if it's obvious or not, but visually, the trajectory that we are seeing, they should look the same. Like, I mean, I'm not saying, of course, the trajectory changes, but the distribution of the, if I take a random sample here that generates a random sample here, each sample will look differently than its image, but if I take many samples here and map it there, or if I just started a lot of Brownian motions at 1, 0, they just would look the same. Okay, now okay, so this is the conformal invariance of Brownian motion, which was proved by Paul Levy in the 40s. Okay, now there's a different way of saying what conformal invariance means. You have a domain, let's say simply connected, doesn't really matter. So you have a domain in the complex plane, and you have a point. And you run two-dimensional Brownian motion until you hit the boundary. So right, it will have this hitting measure, where you hit the boundary, that will have some distribution. It's called the harmonic measure, looked from this point z. Of course, like in this specific example, it's more likely that, right, that it's more likely to hit here than, I don't know, over here. Okay, now let's make a conformal map on this thing. So I tell you that it can be mapped conformally to the disk, to the unit disk, and this Z goes somewhere else. And it's kind of clear that it should be, if this part is somewhere here, then this point should be kind of close to there. And in this new picture, you again can run Brownian motion and get some harmonic measure here, which is it's more likely to be here than over there. Okay, and conformal invariance implies that it's kind of the same, saying that if you look at the measure here and you make a conformal map, then the measure over here is just if you push, if you just copy this measure, right? You take the derivative of the conformal map and multiply it by what is it called? Jacobi determinant. So you just push forward this harmonic measure to here, then you get what if you. And so the push forward of this is the same as doing it in this domain. Okay, I forgot to write it here. You know what a harmonic harmonic function is? The solution of the Laplace equation. So the probabilist way of solving the Laplace equation with Dirichlet boundary conditions. So if you have some domain and you are given some continuous function on the boundary, and you want to find the harmonic extension inside the domain that solves the Laplace equation, then the way to get it, what is the value at this point? Okay, so run a Brownian motion. It hits somewhere. Look at the value. Do it 100 times, and average those values. So and then this will be a good approximation of the harmonic extension here. And so really this harmonic measure gives you, integrating the function on the boundary with respect to the harmonic measure gives you the value at this point. If you learned the Poisson formula for the disk in PDEs, that's a special case of this. Okay, now this is extremely useful because there are a lot of conformal maps. So there is the Riemann mapping theorem, which says that if you have two simply connected domains in the complex plane, which are not the entire plane, then they are conformally equivalent. So then there is a conformal map from one to the other. So however an ugly thing I draw here, it could have fractal boundary, whatever. There's a conformal map that takes it to the unit disk. Okay. And like for instance, if you want to, a more realistic example of doing this, which is actually useful, let's say in the complex plane you have the segment minus 1, 1. And you start a Brownian motion from infinity. I don't know if you can imagine what it is. Let's say you take a circle of radius 1,000,000, and you take a uniform point on that circle of radius 1,000,000, a random point, and you start a Brownian motion and you run it until you hit this minus 1, 1 little segment. Okay, what is the hitting distribution? Okay, well, a way to compute it is that, well, notice that if I take the unit disk, then the inside of the unit disk is conformally equivalent to this domain, to the complement of the unit segment. If I just take this map, this very simple map, so 1/2 times z plus 1 over z, then maps maps the circle to this segment. So it maps minus 1 to minus 1, plus 1 to plus 1, and it pushes the circle, because of the z plus 1 over z. If you think, it's the complex conjugate, and somehow so you just it's the average of this and this. So it pushes the circle into this unit segment, not unit. So into this straight segment, and it maps both the inside and the outside are mapped the complement of the. If you do it from the outside, this point is mapped to infinity in the complex plane. Okay, by the conformal invariance of harmonic measure, if I look at the harmonic measure from the origin on here on the circle, and I push forward with this map F, then the image of this measure will be the harmonic measure on this segment. Okay, well, you can compute, but also I told you it's just doing this. So really, if I take the uniform measure on the circle and do this, project it on -1, 1, what do I get? I get this arc sine law. This is kind of the first example usually in continuous distributions, density functions. Okay, so there is this thing. It's like it blows up near the endpoints, so it's much more likely to hit here and here than in the middle. Anyway, we computed it. And actually, in physics, this harmonic measure is called electrostatic potential, and this blow up of the arc sine law exactly tells you that what is it called in English? This metal rod against the lightning, that collects the lightning. Okay, so the end of the rod collects the lightning much better than the top of your roof, because the harmonic measure blows up here. It's exactly this. Okay, so this little computation is supposed to show that having a conformal invariant scaling limit is something very useful. Now, about 1- and 2-dimensional Brownian motions, these are classical objects. Many things are known about them. Classically, the whole Ito calculus business in financial math is based on them. Okay, for instance, if you draw the 1-dimensional Brownian motion, if you look at the graph of it, the space-time graph, then it's a very wiggly, nowhere differentiable function. This graph has Hausdorff dimension 3/2. If you do it in the plane, then well, it's very wiggly. It almost covers the entire plane. The set of points visited by Brownian motion, they still have a zero Lebesgue measure, but it's a two-dimensional set. Do you have any intuition or knowledge what the Hausdorff dimension is? Kind of. Okay. Okay, but but people notice that there are still some questions that they didn't know how to answer. So let's say you draw planar Brownian motion. So this version is actually, it's called Brownian excursion. It's only in the upper half plane. So it's something like you draw a planar Brownian motion, but from 0, but you condition it to stay in the upper half plane. You can do that. But locally it just looks the same as normal Brownian motion. Over here it doesn't really feel that it has to stay in the upper half plane. Okay, and so Benoit Mandelbrot, the father of fractals, looked at such pictures and observed that, well, if I, what is very visible is this outer boundary, the frontier, the points that are connected to infinity. And looked at, well, this looks the same as a self-avoiding walk simulations. Okay, so they should have the same Hausdorff dimension, which for self-avoiding walk it was conjectured to be 4/3. So what is self-avoiding walk? This is a random curve, which is so here I'm doing it in the upper half plane. So let's do that. So I have the lattice in the upper half of the lattice, and take all possible self-voiding paths of length n. So take n steps that they never come back wherever where you have ever been. Okay, and take, there are many of them. There are exponentially many of them. Take uniformly at random one of them. So that's a random self-avoiding path. And it can be proved that, this definition works only for a given n, when I take n steps. But it can be proved that there is something, an infinite self-avoiding, there's a measure on infinite self-avoiding path. So this is a simulation from that. Okay, and okay, so maybe I can say it now. So these conformally invariant objects that I will be talking about are interesting for the physicists for many reasons. One reason is that they can apply conformal field theory to compute things about them. So this conformal field theory is something that it looks like mathematics, but it's not really. So there are formulas, there are rules, but there is no real mathematical meaning of what the physicists are doing. And often they don't understand these things themselves either. So usually these arguments are like, they have some very strange argument proving that it's 4/3, and they have some other arguments proving some other things, and then they do computer simulations and check which is the right, which is the right answer. Okay, so for the self-avoiding walks, by computer simulations and some physics arguments, it was conjectured this Hausdorff dimension to be 4/3. Okay, and Mandelbrot saw that, well, the outer boundary, the Brownian frontier should also have Hausdorff dimension 4/3. Okay, at that time it was completely out of reach, so that people worked very, very hard to prove that it's bigger than 1. Finally, they managed to prove that it's bigger than 1, but why is it 4/3? Okay. Now, a different model. Okay, so this was random walks, okay, and self-avoiding walk. Now, a different model, the uniform spanning tree. So, take a finite graph, here an n by n piece of the square lattice, and take all spanning trees that it has, right? It has finitely many spanning trees, of course. Take one uniformly at random, one of them. Okay, so this is a sample of that. So this is the uniform spanning tree. Now, there's a beautiful algorithm of David Wilson from '96, how to generate such a uniform spanning tree, which is it's completely amazing. It proves. I don't tell you the exact algorithm, but you can kind of guess after I tell you the thing that if you take any 2 points, and well, in the uniform spanning tree, there's a unique path between any 2 points. Right? So let's say this red is the path between the 2 corners. And so this is a random path in the uniform spanning tree. And this has exactly the same distribution as doing loop erased random walk from here to there. So what is loop erased random walk? I start the random walk, and when I make a loop, so I get somewhere where I have already been to, I erase this loop. Okay, then I go, I erase this loop. Okay, then I go, erase, go, erase. Okay, so chronologically, in chronological order, I erase the loops, and I'm doing this until I get to my target. Okay, so this is the loop erased random walk.
So Gabor, a priori it's not even clear that you get that, right?
In a finite graph, you get. You don't delete from the graph.
Yes.
The graph is untouched. You are doing the random walk on the fixed graph.
Yeah, sure, but it could happen that you screw up in your stuff and keep deleting almost everything.
It's in a finite. No, it's a basic theorem in Markov chains that in a connected graph, eventually you will get to any point. Just by, with positive probability, you just go straight there, and eventually this will happen. Yeah, in an infinite graph, it's more problematic. But no, in a finite graph, this is clear that eventually you get there. Okay, so this is the loop erased random walk. And so this path is exactly the loop erased random walk path. So, you know, I mean, after this, I can tell you what the algorithm is. You know, take 2 points, draw the loop erased random walk, then take a third point, draw the loop erased random walk until you hit what you have already drawn, take a fourth point, draw the loop erased random walk until you hit the tree you have already drawn, and so on, until you have covered everything. Okay, regardless of in what order you take the points, you get the uniform spanning tree. Okay, so this is a very beautiful result. It's not extremely hard to prove. Okay, and now, I mean, it's obviously some fractal-looking curve. You can again ask how long it is, right? In an n by n step, n by n box, you know, how many steps? It's n to some power. What is that power? And so Rick Kenyon proved that it's n to the 5 quarters. So this has Hausdorff dimension 5 quarters, kind of. And the way he proved it is very strange. It's very hard. There is some relationship between domino tilings. So if you take all possible domino covers of this box, so you know, just by 2 by 1 by 2 dominoes, and take uniformly at random one of them. It's called also uniformly chosen perfect matching. That has something to do with spanning trees. There's a bijection between those and spanning trees. And there is some crazy computation. He has to compute the determinant of an n by n matrix, and that has to do with random walks, so some of the Laplacian operator. And anyway, it's some computation that gets this n to the 5 quarters. Okay, but so a different way of thinking of this, which is more related to Brownian motion, is that, well, we got this loop erased random walk from erasing the loops in the random walk. Random walk is converging to Brownian motion, which is conformally invariant. So of course, you know, we just have to find this loop erased walk inside the Brownian motion, and that will be the scaling limit of loop erased random walk. And again, since, you know, we got it from the Brownian motion is conformally invariant. Also, loop erased random walk has a conformally invariant scaling limit. Okay. Now, the issue with this is that, well, if you have worked with one-dimensional Brownian motion, then you know that if you start it from 0, there is no first 0 after 0. There will be, that it goes away, but it immediately comes back. There will be zeros arbitrarily close to 0. So there will be new zeros. There is no first 0. And similarly, if you do a two-dimensional Brownian motion, there is no first loop. You will make loops. There are infinitely many loops on all scales. You immediately make a loop, not a loop, many loops. You immediately make infinitely many loops. So there is no chronological order in which to erase the loops from the Brownian motion. So it's completely unclear what to do. So this is a sample of loop erased random walk with small mesh until from the origin it hits the boundary of a circle, of a disk. But you know, so does this actually exist? The scaling limit of this, is it conformally invariant? Not very clear. Okay, by now we know it does exist, but at the point of my story, you don't know yet. Okay, now percolation. It's just the simplest random graph you can make. So you have some underlying graph. So let's say the square lattice. And for each, in physics, it's called bond percolation. So bonds are the edges, and sides are the vertices. So in bond percolation, for every single bond, you flip a coin. With probability p, you keep it. It stays open. And with probability 1 minus p, you delete it. It gets closed. Okay, so this is the... Okay, and so you get this. You do this independently with this parameter p for each bond. And then you have this... so these are the open, the remaining edges. And then you look at open connected components. These are called clusters in percolation. Okay, and okay, and this is site percolation on the triangular lattice. You do the same with sites, and then you look at, connected components. Whether you can jump to an open neighbor. Okay, and it's not hard to convince yourself that if P, the density of keeping, is very small, then you will only have small islands or small connected components everywhere. And even if you do it on the infinite lattice, there will be only finite. Almost surely there will be only finite clusters. Okay, and if you do it with P very close to 1, then there will be an ocean there will be a giant unique component with small holes in it. Okay, so the critical P is where this behavior changes, this phase transition. So it's the infimum of P values for which the probability that 0 is connected to infinity, well, this is just a shorthand notation for the cluster of the origin. You can get out from 0 to infinity. Okay? So the cluster of the origin is infinite. When it becomes positive. So for small p, this is 0, 0, 0, 0, and then it becomes positive. Or which is the same is the infimum of p values where, not the origin, but somewhere you have an infinite cluster that will have probability 1. Right? So if you can get out with positive probability from the origin, then of course somewhere in the infinite lattice you will have an infinite cluster. This is not completely obvious, but it's not hard to prove that these are the same. Okay, so below PC you don't have infinite clusters. Above PC you have infinite clusters, maybe 1, maybe more. We'll see. Okay, at PC, from this definition, it's not clear what happens at PC. Now, is there an infinite cluster already or not? Okay, so this is just, because the pictures are nicer, side percolation on the triangular lattice. I can take the dual graph, which is the hexagonal lattice. And so instead of coloring the sides of the triangular lattice, I can color the faces of the hexagonal lattice, right? So this is the same configuration, and then just forget the, so coloring the faces of the hexagonal lattice is the same. Okay, and this basic theorem of percolation theory is that, so they computed that the value of PC on a few lattices, for instance, for bond percolation on the square lattice and side percolation on the triangular lattice, the value of PC is exactly 1/2. And at 1/2, there is no infinite cluster. In fact, the probability that you are connected to distance n decays to 0. Right? There is no infinite cluster, so it has to decay to 0. But how fast does it decay to 0? As a polynomial in n. Okay, so this is kind of a critical, this is usually the critical behavior. So when you are below PC, then really the probability to get connected to distance n is exponentially small in n. Okay, and at criticality, it's only polynomial, and above PC, it's already positive. It doesn't decay. Okay, so they proved that there is some polynomial. They didn't prove that there is an exponent. It's bounded between polynomials. Okay, and above PC, there is a unique, almost surely there's a unique infinite cluster. Okay, now, why 1/2? That's very easy to understand. So, physicists knew this was 1/2 way before Harris and Kasten. So, if you take an n by n, well, really an n by n plus 1 rectangle in Z squared, and so the blue is a percolation configuration. Okay, and then I take, okay, maybe it's not very, okay, actually the red doesn't really matter, but so let's say I take, okay, so this is a 3 by 4 rectangle, And I do percolation on this at okay, so if I do percolation at density P, okay, and I'm asking the question, what is the probability that I can get from this side to that side? Okay, so I do, I don't know, P equals 0.4. This is a random sample of that. Okay. Now, just to remind, so this is the picture how it is drawn. Just to remind myself, I mean, the color on this and that, they don't influence whether I can get from the left to right, right? So just to remind myself that I want to get through the orange from this side to that side, I can just take it to be open. It doesn't influence the. Okay, so this is an orange configuration at density P. Now, I could also look at the dual configuration, which is I take the dual lattice. Okay, I'm doing it this way. Okay, it's there. The dual lattice is there, right? Connect the faces. Okay, and each edge has a dual edge, the one rotated by 90 degrees. Okay, and wherever I don't see an orange edge, I draw it. Well, in the picture it's blue, but now it's white. Okay, and just now. Okay, it's kind of obvious, but a proof is needed. But there are exactly two cases. Either I can get, there is an orange path from left to right, and if there's a white path from top to bottom. Okay, so if there's a white path like now, then this white path stops the orange crossing, and vice versa. So just remind myself that. Okay, and so either there's a red left to right or a white top bottom. Now the white configuration is just again percolation on a 3x4 grid, right? Just what is the probability that this edge is open? Well, this is open exactly when this was closed. It was closed in the orange. In the orange, it was closed with probability 1 minus p. So this is open with probability 1 minus p. Okay? Which means that the probability at p of an orange left-right crossing plus the probability at 1 minus p of a white top-bottom crossing is exactly 1. Right? Because exactly one of them happens. Okay? So they add up to 1. Now, if I take p equals 1/2, then whether I have this left, right, or that top, bottom, then p equals 1 minus p. So these probabilities are the same, right? Okay, so at 1/2, they are the same and add up to 1. So they are each is 1/2. Okay, so what did we learn? Is that the probability of a left-right crossing in an n by n plus 1 square rectangle is exactly 1/2 at p equals 1/2. The probability of crossing is exactly 1/2 regardless of n. Right? It doesn't matter how big I took. I either get through or I don't. Okay, and okay, the corresponding version for the triangular lattice is, if you know the game of hex, this is a hex board, and then the duality, so either there's a black left, right, or a white top, bottom crossing, exactly one of them. And so you don't have to take a different graph. It's on the same graph. It works. Okay, now, so at p equals 1/2, something nice is happening. There is this probability of crossing is 1/2 regardless of size. There is this scale invariance. It doesn't matter how big a square I'm looking at, it's 1/2. Okay, and then actually it was proved that at 1/2, so this is not specific to the square. If you take any okay, let's say, so actually if you take any rectangle with a fixed aspect ratio, so it's an n by L times n rectangle, then the probability of the left-right crossing is bounded away from 0 and 1, regardless of the size n. Okay, right? So the probability of getting through this, this is n, this is 3n. It doesn't decay with n at 1/2. This has a uniformly positive probability. Of course, it's less than 1/2 than it was in the rectangle, but it's uniformly positive. Okay, and once you have this, it's clear that the p equals 1/2 should be the critical value. I mean, intuitively it's clear, because how percolation should look like is that, above the critical value, there should be a giant, so when p is bigger than 1/2, there should be a giant black component with small white islands. And, given the p bigger than 1/2, there should be a typical size of the holes, right? Of course, I mean, right? Of course, right? Why not? Okay, so it should be a typical size. And if you take a box which is much bigger than the typical size of a hole, of the holes, then right, if you put a box here, then of course you have a left-right crossing through the infinite cluster that intersects the box. So right, if you took a large enough box, then with probability very close to 1, you should have a crossing. And similarly, below the critical point, when there is only just finite islands, where there is a typical size for the islands, if you take a huge box, which is bigger than the typical size, actually this typical size is called correlation length in physics. So given p, okay, so let's say if I take delta equals 1/2, no, that's not good. Anyway, there is some exact definition of correlation length. It doesn't matter for now, because we won't have time anyway for that. Okay, so if I take a big box, below criticality, the probability of a left-right crossing should go to 0. Actually, quickly, it should go to 0. So if however big a square I take, it's always 1/2, where that must be the critical point. Okay, so that's why this.
Gabor, was this a physics proof or a math proof?
This was a physics proof. This is a completely physics proof. Yeah. So, yeah, for the math proof, well, I mean, this picture is true, but you have to prove that this picture does hold. So in Kastan's proof, he actually proved that this is how it looks like, and hence this argument makes sense. But yeah, before that, no. Okay. Now I'm getting to the main point, is that, okay, this is critical percolation on different lattices. So maybe it's actually not that well visible, but although they are different lattices, these critical clusters should look the same. I don't know, the macroscopic behavior, like how wiggly this is. Okay, there is some discrete thing. Okay, anyway, maybe it's not perfect, but anyway, there's a universality conjecture, which is that if you take different planar lattices, then the value of PC really depends on the lattice. It was 1/2 in these two cases, but that's an accident. If you take a side percolation on the square lattice, so recoloring the sides of the square lattice, then PC is about 0.53, if I remember, but no one knows the exact value, and probably it's not a nice number. And actually there's a conjecture that the value of PC depends only on the local structure of the lattice. However, once you look at the critical density, then regardless of on which lattice you are doing this, the macroscopic behavior is the same. So what do I mean by macroscopic behavior? So let's say if you look at, clusters are finite, but if you look at the large finite clusters, their boundary have the same dimension, the same length. Okay, it should be 7/4. At criticality, the probability that we are connected to distance n, I told you that it decays as a polynomial. On all lattices, it should, on planar lattices, it should decay like n to the minus 5/48. If you look at, you can look at off-critical exponents too. So if you go a little bit above PC, then the probability of 0 being connected to infinity is already positive, but small. How small it is? It's epsilon to some another power, 5/36. And so again, like in the case of self-avoiding walk dimension, 3/4, these numbers were conjectured by physicists with this conformal field theory computation. So these are rational numbers because these are really kind of dimensions, of some irreducible representations of Virasoro algebra, which is in some infinite dimensional algebra in conformal field theory. So whatever they are, but these are, there's a good reason why these are rational numbers. Okay, and an analogy is that the simple random walk was converging to Brownian motion on all lattices, right? Because the central limit theorem works whatever the jumps are. Okay, so here also, whether square lattice or triangular lattice, we should sort of see, once we have some scale invariant stuff going on, because at criticality we saw that there is this scale invariance, the probability of crossing didn't depend on the size. Once we have this scale invariant stuff, somehow we should see a universal scaling, a universal limit. So somehow these pictures should be universal. And this is the conjecture in many models in statistical physics. At the phase transition point, the place of the phase transition point may depend on the small local definitions in the model, but there are many models that differ only in their local definitions, but kind of the same. They should have the same critical exponents. They should look the same. Okay, and actually, it was proved by Smirnov. He got half a Fields medal for this. He got the other half for a similar but different result. Okay, so critical percolation is conformally invariant, just like Brownian motion. What does that mean? So his proof works only for critical side percolation on the triangular lattice. There is some combinatorial miracle that makes it work only there, but it should be true on any lattice, critical percolation on any lattice. If you take a simply connected domain with 4 marked points on the boundary, and you draw a very fine lattice on this domain, and look at the probability that inside the domain, in this small lattice, there's a left-right crossing. So you can go from here to there. Okay, what is this probability? When n, the 1 over n, the mesh goes to 0, this thing has a limit, which is strictly between 0 and 1. And this number, so the probability of having the left-right crossing. So this has a limit. It's strictly between 0 and 1, and it's conformally invariant. If you make a conformal map from here, so any domain with 4 points is conformally equivalent to a rectangle of a certain aspect ratio, or many things. So okay, so an equilateral triangle with one side this and the other side is that. Okay, so you make a conformal map, and then you redraw the lattice, compute this this limit in this new domain, and you get the same number. Okay, and so actually here. So what is the number we get here? So that's why I drew it here. So if this is 1 and this is x, okay, strictly between 0 and 1. Well, of course, if x is bigger, then the probability of a left-right crossing is bigger. Okay, so this function as a function of x is monotone. When it's 0, well, then it should be 0, because being connected to a very small thing should be negligible. And when it's 1, then it's actually 1, because already here you get connected. Okay, so tell me a function which is strictly monotone from 0, 1 to 0, 1, and it's 0 and 0, 1 at 1. Okay, the identity. Okay, so this is the truth. So the probability of being connected in critical percolation from here to there is x. Okay, and okay, I really should stop. So, okay, so this type of conformal invariance is like this harmonic measure, right? It looks like that formulation, that the harmonic measure is conformal invariant. Now, if you want something that, Brownian motion, there was this random object there that was, if you mapped it, it looked the same. So also, if we map clusters, critical clusters, they should look the same. And there should be some continuum object, like the Brownian motion, in the plane. Now, it's a little bit hard to define what continuum critical percolation is, because it's easy to prove that it cannot be a random black and white coloring of the plane. Well, one issue is that you kind of should flip a fair coin for every single point in the plane, and it's just too many coin flips. It's not a good sigma algebra. But okay, it could be some random coloring, I shouldn't flip everywhere. But anyway, it doesn't work. So there is no good random black and white coloring. There are other ways. You should look at the cluster boundaries and prove that if you look at all the cluster boundaries together, they converge to some collection of cluster boundaries in the continuum. Okay, and so this conformal invariance is not just some beautiful thing, but it actually makes it possible to compute a lot of things. Okay, so this is this Schramm-Loewner evolution that here. Okay, I will finish soon. It says that if you have in the plane, if you have some non-self-intersecting curve, so the Brownian motion is not good, but the outer boundary of the Brownian motion, that could be good. Okay, or in percolation, this is the interface between a black and a white cluster, like this red thing here. So if you have some curve, which is if it is conformally invariant, well, someone, typically Smirnov, has to prove that it's conformally invariant, and it has some spatial Markov property, which whatever it means, it's kind of, things in all these probabilistic models have this Markov property. It basically says that, once you know, it's kind of the distribution. It's like a Markov chain. Is that the distribution in the future depends from the past only through the present. This is a Markov chain, right? And in the plane, the corresponding thing would be like the configuration inside the domain depends from the outside only through the boundary of the domain. And if in percolation, well, it's independent, so it doesn't depend on anything. So there it's obvious, but there are other models when it's less obvious. So once you have these two properties, and it's a non-self-intersecting curve, like an interface, it can be described by some SLE, some meaning by an SLE kappa with some value of kappa. So this is a one-parameter family of random curves in the complex plane. And really, so this SLE is something that you can do computations with. So the way it works is that it encodes, so you have this complicated curve in the plane, and it encodes into a curve on the boundary of the domain, just a one-dimensional curve process on the boundary. It's like when you drive a car in the upper half plane, if you just record when you are moving left or when you are moving right, the steering wheel. So there's a one-dimensional data to encode this. And so this is something, this is the Loewner part. So Loewner used this to describe conformal maps. So using conformal maps, if you have a curve like this, you kind of map it conformally to the upper half plane and see what happens. So there's a way, so for any curve like this, okay, you kind of think of it as you cut it through as a slit domain, and you map it to the upper half plane. And from this, so any growing curve, you can describe it by a curve on the boundary. And what Oded realized was that, of course, he didn't know about the Loewner chain himself before. I mean, he also invented that part. But anyway, what he realized is that this Markov, this conformal invariance and the Markov property makes it that whenever you have such a curve, then this thing on the boundary must be a Brownian motion, a one-dimensional Brownian motion. Okay, and the kappa is just how fast this Brownian motion is. Okay, and then a lot of questions about this curve can be translated into questions about this Brownian motion and to Ito calculus. So this is, and then you can compute these critical exponents and many things. Okay, just to get back to, okay, this is the last slide. Okay, to get back to Mandelbrot's conjecture. So the way Loewner, Schramm, and Werner proved this 4/3 is that they proved, it sounds a bit crazy. So if you take, remember these two things, where are they? Okay, so this Brownian excursion in the upper half plane, this Brownian motion in the upper half plane, and the self-avoiding walk. Now, that self-avoiding walk has a scaling limit that's absolutely not known. It could, well, now there's a proof that it's not completely space-filling and it's not completely straight line. But these are, I mean, very little is known about this. But what is known that if there's a conformally invariant scaling limit, that must be, by this characterization, it must be SLE with some kappa, and the value of kappa is known, what it should be. Now, 8/3, it should be 8/3. Now, what they proved is that if you take 5 independent copies of Brownian motion in the upper half plane, so these are 5 independent copies, this mass is 5 independent copies. Okay, and you look at the right boundary of this stuff. Okay, it sometimes it goes with one of them, sometimes it goes with the other one. There are 5 of them. So clearly the dimension of this stuff is the same as the dimension of one of them, of the boundary of one of them. Okay, so if you have 5 independent copies of this, and if you take 8 independent copies of SLE 8/3, which is this nice non-self-touching curve driven by some Brownian motion on the boundary. So you have 8 independent copies of those, and you look at the outer boundary of that. These are exactly the same. They have the same distribution. Okay, because they both have some properties, some very nice algebraic properties that identify this thing uniquely. So there is just one such thing, and they both satisfy these. So they are the same. Okay, and you have these 8 SLE 8/3, and for SLE 8/3, I told you, you can make computations. You can do computations or make. Anyway, you can compute. For instance, the Hausdorff dimension of SLE kappa is 1 plus kappa over 8. So for 8/3, the dimension is 4/3. If you have 8 copies, well, it doesn't matter. Still, it's 4/3. So also here is 4/3. So, okay, this is the Fields Medal of Werner. Schramm didn't get a Fields Medal because he was 3 weeks too old. So his co-author got it. Okay, so this is how it works. Okay, I stop. Maybe I show one movie, okay? Because I didn't say anything about what I'm working on. Well, maybe not this. Maybe I'm doing this. Except I don't know how to press the play button. No? Okay, sorry. Okay, is it visible? Okay, maybe the other one would have been better visible. Okay, so so what is this? This is critical percolation, black and gray, black and white, and the red thing is the cluster of the origin. And the dynamics is I'm doing dynamical percolation, which is, first I took percolation, everything is black with probability half, white with probability half. And now each side has an independent clock, an exponential clock. According to a Poisson process, they switch between black and white, independently from each other. So at any given time, at time 1.7, you always see critical percolation, right? So it's exactly critical percolation. So the probability, so this is dynamical percolation. This is what we are seeing, and I'm always looking at what the cluster of the origin is. So this is this red thing. Now, there's an interesting thing that this almost sure thing in probability. You always you say it. It's some boring thing that you always have to say, that it's not sure but only almost sure. Now, in this case, this actually matters. So I told you that at the critical point, almost surely there are no infinite clusters. Okay. Now, but we have this continuum time dynamics. It's true that at any given point, the probability of having an infinite cluster is 0. Okay. But there are a continuum number of them. I cannot take a continuum number times. A continuum times 0 is either 0 or more than 0. It's not clear. So there could be random times, random exceptional times, where actually this probability 0 event does happen. So there could be times when there is an infinite cluster, when the origin gets connected to infinity. And that actually happens. So that's a theorem of us with Garban and Schramm, that there are exceptional times, and we know how many of them are. Their Lebesgue measure on the time has to be 0 by Fubini. It has 0 probability, so their measure has to be 0. But it's a random Cantor set, a random Cantor set of Hausdorff dimension 31/36. And this is what. So there is this movie. What really should be obvious is that when the cluster is small, then it's kind of stable. It doesn't move a lot. But when the cluster is big, then it moves very quickly. So somehow this so somehow changing a few bits, changing the configuration on the large scales completely. So there are many almost independent trials to see something strange, and you actually do get exceptional times. Okay, but this is a hard proof that uses Fourier analysis, which, well, that's another. Okay, that's a semester. Okay, thanks.